Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 5, Lesson 4, Transformations of Piecewise Functions. After this lesson, you'll be able to graph and analyze transformations of these piecewise functions. So just remember in Topic 3, when we did transformations of linear functions, the rules will apply in the same way. For the model and discuss, we have this graph. It's a step function. We can see that it is a floor function because we have the lower end equal to. Cleo takes 3 one-hour classes at a community college. The graph shows the time she spends in each class. Next semester, each class will start an hour later. How will this change the graph? Well, so that means instead of starting at the first class starting at 8 a.m., it will start at 9 a.m. So we won't have this section anymore. The first class will start at 9, it'll go to 10, or just before 10. The next class will start at 10, we'll go to just before 11, and the third class, so then this would be, these would change also. Second and the third class then would start at 11 and go just before 12. Part B, starting in the fall, Cleo will take 3 classes in a row, with the first starting at 7 a.m. She says we can update the graph by moving all 3 steps of the function 1 unit to the left. So 1 step to the left, is that going to be right? Well, no, she's thinking 1 hour, but if we're looking at the intervals, each grid, each square is worth 30 minutes. So she's going to need to move it over 2. Okay, so this one would need to start over there. And this one would need to start over here. And this would need to move over 2 units. So how do constants affect the graphs of piecewise functions? Example 1, Kareem's taxi company charges a base fare of $5 plus $1 per mile, or part of a mile. Okay, so we could think it would look like y, the total cost would be 1x plus 5, but remember, he's charging for part of a mile, so we have to round up. So we do have a ceiling function instead. So then our function, I'm going to write it in function notation, would be ceiling function of x plus the 5. Okay, since we're rounding up and we're including part of the next mile, we have that ceiling notation. He's comparing his function to other taxi companies. So that's what's in the table. This data in the table is other taxi companies. Using a ceiling function, we can graph this on our graphing calculator and we can compare it to the data in our table. So get out your graphing calculators. We're going to do 2 things. We're going to plug in this data into L1 and L2, and then we're going to plug in this equation into y equals, and we're going to compare those 2 graphs. So on your graphing calculator, let's first put in our table. So you're going to go to Stat, hit the Stat button, and Edit. Okay, and list 1 is going to be our distance, the x values or the input. So type in 0.7, 0.5, 1.3, 1.9, 2.5, 2.75, whoops, 3.25, 3.6, 4.3, and 4.5. And then L2 will come from our outputs, our y values. That's the cost, the total cost of the trip. 1.85, 2.9, 2.15, 3.05, 4.5, 4, 5.1, 5.1 here, then 6.5, and then 5.75. So that's a good check. Make sure that your tables have the same amount of values in each one. Okay, and then I'm going to go set up my stat plot. So up here above the y equals, hit second y equals, and we need to make sure our plots are on when we do our tables. So turn plot 1 on. I'm going to highlight on. I want it to be like a scatter plot. I don't want to connect the lines. I want a discrete graph, and then my x values are coming list 1, my y values are coming from list 2. That's fine. Actually, I'm going to change the color. Okay, so it'll be red, and we can see the graph. There's the data points. Okay, going to y equals, we're now going to type in the equation that Kareem has for his. So remember, when we're doing a ceiling function, we use the math button. So there's no scale factor in front of it, so we just need to go to the math button, arrow over to numbers, hit option number 5. This is our ceiling function. Type in so that parentheses is going to represent the ceiling brackets. Type in our variable, close the bracket, and then +5 for the base fare. And then we can graph that one. That graph will show up as blue on our graph. So here we go. There's the two graphs. You can see our step function with Kareem's equation, and then there's the data from the other tax companies. What do we notice? Kareem's graph is above the other companies, so he's charging more. His costs are higher than the other companies. So what does he need to do? He probably could or should lower the base fare. So if he lowers it to $2 instead, that will change his equation. So let's go back to y equals and change his equation. Instead of his base fare being 5, let's lower it to 2. Actually, let's just put it on another line and we can compare it. I'm going to do green. So I'm going to show you all 3 graphs at once. So I'm going to type this one in again. Arrow over to numbers, 5, x, close my parentheses, and now the base fare is going to be 2. Let's graph that. Okay, so the green graph was where he lowered his base fare to $2, and that is going to be right in line with the other companies. Okay, so that would be a better function to use for Kareem. For try it number 1, how would the graph be affected if he increased the base fare to $6.50? Well, it would be even higher than the first blue step function, okay? It would be shifted up 1.5 from the first function, or the first graph, the blue graph, okay? If we're increasing the base fare, then all the outputs would increase or go up by 1.5. Vertical translations of the absolute value function. So just like with linear translations, we can apply the same rules to the absolute value function. Remember, an absolute value function is a specific type of piecewise function. So we are adding a constant to the output, okay? So outside the parentheses, we can think of those absolute value lines as special parentheses. So here we have a change to our output. We are decreasing the output by 4. So when our input is 0, our output then is decreased by 4. It goes down 4 units. Same with g of x. Now we're increasing it by 2. So the blue function is the parent function where we start at 0. When our input was 0, our output was 0. But with g of x, we add 2. So we've shifted the graph up. So remember, changes to the outside of the parentheses change the output. We are moving vertically up or down. So if it's positive, we're going up. And if it's negative, we're going down that many units. The vertex stays on the same axis of symmetry. The axis of symmetry does not change. Okay, it's just moving up or down. Try it number 3. For each function, identify the vertex and the axis of symmetry. So we have a parent function. So there's our basic absolute value function that starts at 0, and all we're doing is adding 3 to the output. So this is going to shift the graph up 3 units. And where will the vertex be? Well, instead of the vertex being at 0, 0, it's going to be at 0 and up 3 units. The output, or the y value, has added 3. So instead of being at 0, it's going to be at positive 3. Where's the axis of symmetry? It's still going to be right on the x-axis or the y-axis, so where x equals 0. For part B, again, we're not changing the input. We're making a change to the outside of the parentheses. This time we're shifting the graph down 2 units. We're changing the output and subtracting 2 from each y value. So the vertex would still be at 0, comma, but instead of being at 0, 0, we've subtracted 2 from the output or from the y value, so now our vertex will be at negative 2. The axis of symmetry still is on the y-axis at x equals 0. So we're just moving vertically up or down. What happens when we add a constant to the input? So now we're changing inside the parentheses, okay? We're changing inside the parentheses. And so remember, when we're doing this, we have to think opposite, okay? In order to get g of x to match up with the parent function, we have to move to the right and then if we move to the right, our input is 4 more to the right. Then when we subtract 4, we're back to the original function. So think opposite. If it's -4 inside the parentheses, that means we have to move our whole input to the right 4. So again, look where the outputs are the same at 0. My input is at 4. And then so my x value is 4. If I subtract 4, it gets me back to 0 where the parent function is. Now what's happened to the axis of symmetry? The axis of symmetry has shifted now because we're changing the input. We're changing the vertex itself. So now the axis of symmetry is going to be where that vertex is, where that shift is happening. For try it number 3, let's identify the vertex and the axis of symmetry. So again, we're changing inside the parentheses. So we're going to think opposite direction. If it's -3, that means we're moving the input to the right 3, so that when I subtract 3, I'm back to 0 at the parent function. So that makes our vertex, now it's going to be 3 units to the right. So our x value increases by 3. So our vertex would be at 3, 0. Our axis of symmetry is then going to be where that new x value is. Where is the vertex? At x equals 3. So we'll have a horizontal axis of symmetry at that value where the vertex is. Part B, inside the parentheses is +5. That means we're moving to the left 5, so that when I add 5 to -5, I get back to 0 where the parent function is. So that means my input, my x value, is going to be 5 less, or at -5, 0, there's my vertex. And the axis of symmetry, remember the vertex is on the axis of symmetry, so the line would be at -5. A vertical line at -5. Example 4, vertical and horizontal translation, so a combination, and we're going to be looking at what's called vertex form. Okay, so when we have changes to both inside and outside the parentheses, we can identify the vertex. Here are our 2 graphs. The blue function is the parent function. Okay, so what's happening to g of x? G of x, we have a change inside the parentheses. So first what we did was we moved it to the right 4, and then we moved it down 2. So the vertex goes from 0, 0, moves to the right 4 and down 2. Here's our new vertex. Notice how they wrote it. The vertex is 4, -2. Inside the parentheses is the opposite of 4. So that's what vertex form tells us. It's set up to be the opposite of h, or the opposite of the input value, plus k, and that's the output value. So just remember that's the opposite of whatever the vertex is, whatever the x value for the vertex is. For j of x, we have shifted to the left 5, because that's inside the parentheses, so the horizontal shift is to the left 5, and then we go up 1. So our vertex started at 0, 0. We go to the left 5 and then up 1. Here's our new vertex at -5, 1. And you can see it's the opposite. What's the opposite of -5? +5. So as we write it in function notation, we do the opposite of the x value for the vertex. Plus k is on the outside of the absolute value lines. So it'd be really good to memorize vertex form because you can look at that function written in that form and identify the vertex. Try it number 4, find the vertex of each graph. So it's written in vertex form, x opposite h plus k. Okay, I'm saying opposite h instead of -h because a negative sign just means opposite. So I want you to be thinking this is opposite of the h value or the input value. Okay, so what's the opposite of -1? +1. And then k is just whatever is written. So there's the vertex. For the second one, what's the opposite of h? Opposite of +2 is -2. And then k is whatever is outside. That doesn't change. So there's the vertex for g of x. And we can think, we've moved it to the left 2 and up 6. So if we move it to the left, then that means we're at -2. We're to the left of 0. So that does work. You can always double check yourself by drawing your arrows for where the graph moves. Example 5, how does a constant in front of the absolute value, so we have that scale factor, how does that constant affect the graph? So now we're looking at stretches and compressions. Remember, if it's outside the parentheses, we're changing the output, okay? And if it's less than 1, we're making the output smaller. And if it's greater than 1, we are making the output bigger or more stretched out. And don't forget, we have that special rule with the negative sign. The negative means we flip it. So instead of being upward facing, it's going to be downward facing. We've just done the opposite slope. So let's take a look at what we have. The blue, again, is our parent function, absolute value function. G of x, we have a scale factor outside the parentheses. So I'm changing the output, and I'm just taking the output and cutting it in half. So let's look. Where is the output? Right here. Okay, when x equals 2, instead of being at positive 2, what's half of positive 2? Now my output for the new function is at half of that, which is at 1. Okay. Could look at 4. If my input is 4, my output would be 4 in the parent function. What's half of 4? Now my output would be at 2. So we've compressed it. This is a vertical compression. We've smashed the graph down closer to the x-axis. Okay, we're just smashing the graph, the parent function, down close to the x-axis. It got wider. For g of x, the second one, we have a negative 4 as our scale factor. So the negative tells us we flip it. It's the opposite slopes. Okay, so now it's downward facing. And the scale factor, then, we're multiplying the output by 4. So let's take a look. Where the output is here, we'll compare there. Do a better one. So at x equals 1. Originally, my output was at 1. If I flip it, then it should be at negative 1, but then we're multiplying it by 4. What's 1 times negative 4? It would be at negative 4. So our output has become the opposite and multiplied by 4, so we've stretched it vertically. We have flipped it and stretched it vertically. So it should be skinnier or narrower. Try it number 5. Compare the graph of each function with the graph of the parent function. Okay, so we have a change to the outside. We have a scale factor. That means we are shifting vertically or compressing or stretching it vertically. Since it's greater than 1, we're multiplying the outputs by 3, so that means the output is going to get stretched out. Okay, so this is going to be a vertical stretch. It's still going to be upward facing because it's positive. So it will be narrower. The graph will have a narrower V. For part B, we have a negative, so now it's flipped. It's going to be downward facing. And the scale factor is less than 1, so we're taking whatever the output is and making it smaller. So this is a vertical because it's happening on the outside of the parentheses, so we're changing the output, changing the y values. This is a vertical compression. We're making it wider. We're making the output smaller, but then the graph will look wider. Example 6, putting it all together. So now this is full vertex form. So you'll want to memorize this. This is just the basic formula for vertex form. A is whatever the scale factor is for any vertical compression or stretches. Opposite H will represent your change horizontally, your translations horizontally. Plus K will represent your vertical translations, moving the graph up or down. So remember, opposite H, comma K is your vertex. I'll write that here. I like to say opposite H, comma K. That will give you the vertex. Okay, so our parent function is usually at 0, and we go up 1. It's just, okay, there's our parent function. And here's the graph that we're drawing for g of x. So we have, let's identify the shifts. Let's first go, we have a plus 4. What does that mean? Plus 4 is vertical shift. We're going up 4. The plus 3 inside the parentheses. Think opposite. We're shifting it to the left 3. The negative tells us it's downward facing. And then the 2 scale factor, we're multiplying the output by 2, so every output gets doubled. This is a vertical stretch. Okay, so we're putting that all together. So instead of being at 0, 0, we're shifting to the left 3 and up 4. So 1, 2, 3, up 4, here's our vertex. So the first thing you're always going to do is plot the vertex. Opposite h, I like to write it like this so I remember to do the opposite of whatever's inside the parentheses. What's the opposite of positive 3? Negative 3, comma k. So here's our vertex. Plot your vertex, and then this is your axis of symmetry. That's important. Okay, so draw your axis of symmetry. You can use a highlighter, you can use a dotted line, very light, just to help you see where your line of symmetry is. And then you can just pick points to evaluate with that function. You can pick input values. Why not use 0? Why not evaluate f of 0? So if we plug this into our formula, let's find out. What's the output when the input is 0? So I'm going to plug it in. Negative 2 times the output of, the absolute value of 0 plus 3 plus 4. Negative 2 times the absolute value of 3 plus 4. The absolute value of 3 is 3. So negative 2 times 3 is negative 6 plus 4. My output is going to be at negative 2. So when my input is 0, I have a second point. My output would be at negative 2. Plot that point. All I did was pick a value for my input. That's pretty easy. I often do 0 or negative 1. And I plot that point. So here's that point. And now, since I know it's symmetrical, because it's the absolute value function, and I have an axis of symmetry, I can just reflect that line. So that line was 1, 2, 3 units to the right of the axis of symmetry. I'm going to plot another point, 1, 2, 3 units to the left. So here's my reflected point at negative 6, comma, negative 2. And there I have 3 points. That's enough. That's sufficient to draw my absolute value function. You could do another point if you wanted to be more accurate. We could evaluate when x is negative 1. We could do the same thing. Evaluate f of negative 1. Negative 2 times negative 1 plus 3 is positive 2 plus 4. So this would be negative 4 plus 4. That would be 0. So I have a new point at negative 1, comma 0. Plot that point and then reflect it on the opposite side of the axis of symmetry. You could even do positive 1. You could evaluate f of positive 1, get your point, and reflect it to the other side. Part B. Now we're going to move in the opposite direction. We're going to have the graph, and we're going to come up with the function, the equation for the graph. And that means we need to identify the constants a, h, and k. So remember, we're going to write our formula in vertex form. F of x equals a times x opposite h plus k. You'll want to have this formula memorized. And we need to come up with numbers just like with y equals mx plus b. We have to have numbers for everything but the input and the output. So first, let's identify the vertex. What is the vertex of our graph? Well, it is at 4, comma 1. Okay, that's h, comma k. To plug it into my formula, that's opposite h. So then I'm going to have x minus 4 inside parentheses plus 1. Okay, so I have now just to find a. How do I solve for a? Well, again, we can pick values to evaluate and solve for a. So let's pick another point on our graph that we can perfectly identify, like, for instance, here. We can identify this point. This is 5, comma 4. We know that point exists on the graph. So let's plug that in. Remember, the output is 4, the input is 5. So 4 equals a, I don't know yet. My input, my x value is 5 minus 4 plus 1. Okay, I'm just going to do the math and solve for a. 4 equals a times the absolute value of 1 plus 1. Subtract 1 from both sides. 3 equals a times 1. A equals 3. So now I know my scale factor, and then I can plug that into my formula. Okay, that goes in the place of a. You could pick any point on the graph. You could have chosen this point. You could have done it with 3, comma 4. you would have gotten the same value. I'll show you really quick. So the output was 4 equals A times the absolute value of 3 minus 4 plus 1. Okay, 3 minus 4 is negative 1 plus 1, subtract 1, subtract 1. 3 equals, the absolute value of negative 1 is positive 1. And so A would still be 3. So as long as the point, you could even use this point here, 6, 7. As long as it has an exact coordinate, you can plug that in to solve for A. Let's try it. Number 6, write the function. So first, what do we need to do? The easiest point to identify is the vertex. This gives us 2 parts of our equation, 2 out of the 3 parts that we need to know. Remember, I'm going to write it here again. F of x equals absolute value, A times the absolute value of x opposite h plus k. I need to replace numbers for A, h, and k. If I find the vertex, I already know 2 of those. I already know h and k. So my vertex here is at negative 1, 2. Remember, we plug it into our formula. It's opposite of the input, so then it would be plus 1 inside the absolute value, and k would be positive 2. Double check. That means I moved to the left 1. Yes, I shifted my graph to the left 1 and up 2. So you can always check using your transformation rules. Okay, now I need to solve for A, and I'm going to plug in a point from my graph. Let's use this point, 1, 5. So my output was 5. I don't know A. My input was 1 plus 2. 5 equals A times the absolute value of 2 plus 2. Subtract 2 from both sides. 3 equals A times 2. Divide both sides by 2. My coefficient, or my scale factor, is going to be 3/2. So the function we would write then in vertex form, f of x equals, replace A with 3/2 times x plus 1 and plus 2 outside of the absolute value lines. Okay, for part B, write the function of the graph after a translation 1 unit right and 4 units up. Okay, so it's the same graph, so it's going to have the same scale factor. So it's still going to be 3/2 as my scale factor, but I've shifted it 1 unit to the right. From here, now it's going to be at 0. Okay, so that just becomes x plus 0 inside the absolute value lines. And 4 units up, it's from here, I go 4 units up, 1, 2, 3, 4. So now my vertex is going to be there, right? Same scale factor, but now my vertex is going to be up 4. So it's up 4 from the graph, but from the parent function. Remember, the formula is comparing it to the parent function. So where is that vertex going to be? At 0, 6. So I need to show that it will be at 0, 6 with the same scale factor. So here's part B. We made it to the concept summary for transformations of the absolute value function. Remember, you'll want to memorize vertex form. Okay, you'll want to memorize this formula and how to identify the vertex from it. Opposite h, k. Opposite h, k. And then how the translations happen. Okay, inside the parentheses, we go the opposite direction. Outside the parentheses is vertical, up or down. Okay, and the scale factor tells us if we stretch it or compress it. Here's an example. We see that we've moved from the parent function to the left 3 and up 4. So to the left 3, starting at 0, 1, 2, 3, then up 4. Here's my vertex. And then the scale factor is -2, so that means the negative, we reflect it downward. And scale factor is greater than 1, so it's a vertical stretch. The output is going to be stretched out more. And you can plug in any value for x to solve for the new output. If you have any questions, put them in the comments. Make sure and like and subscribe, and come back for topic 6.